Hello there. In this lesson, we're diving into one of the most fundamental aspects of programming, which is performing calculations with Java. Understanding how to work with numbers and basic arithmetic operations is absolutely crucial because every real-world application you'll ever build will need to process numerical data in some way. In this series, we'll cover 4 key topics. First, we'll explore basic arithmetic operators, where you'll learn addition, subtraction, multiplication, division, and the special modulo operator. Second, we'll examine operator precedence to understand how Java evaluates complex mathematical expressions. Third, we'll dive into type promotion in arithmetic to see how Java automatically handles mixing different number types, like integers, doubles, and floats. This prevents data loss and ensures your calculations work correctly. And finally, we'll tackle understanding integer division, which can catch even experienced programmers off guard and is one of the most common sources of bugs in Java programs. Let's build a basic calculator to explore Java's arithmetic operations. I'm starting by creating a class called Basic Calculator inside the JavaPro module 3 package. The first thing I need to do is establish some numbers to work with. I'm going to create 2 integer variables to store our data. I'll call the first one number 1 and assign it the value 20. Notice I'm using a meaningful variable name here because in real programming, you want your code to be as readable as possible. For the second variable, I'm going to create another integer called number 2 and give it the value 8. These 2 numbers will serve as the foundation for all our calculations. Now I want to verify that our variables contain the correct values, so I'll print them out. I'll display the value stored in number 1, then do the same for number 2. I'm also adding an empty line to create some visual separation in our output. Next comes the interesting part, which is performing all the basic arithmetic operations. I'm going to create 5 new integer variables, each one storing the result of a different mathematical operation. First, I'll create an addition variable that adds our 2 numbers together. Then a subtraction variable that subtracts number 2 from number 1. For multiplication, I'm multiplying both numbers together. The division variable will divide number 1 by number 2. And finally, I'll create a remainder variable using the modulus operator, which gives us what's left over after division. Now I'll display all these results in a clear, formatted way. For each operation, I'm printing out the calculation in a readable format, showing both the numbers, the operation symbol, and the final result. This makes it easy to see exactly what calculation was performed and what answer we got. When we run this program, we'll see all 5 basic arithmetic operations in action with our chosen numbers. Let's execute this and observe the output. As you can see, our program displays the initial values. Number 1 equals 20 and number 2 equals 8. Then it shows us each arithmetic operation. Addition gives us 28, subtraction gives us 12, multiplication gives us 160, division gives us 2, and the remainder operation gives us 4. This remainder of 4 makes sense because when you divide 20 by 8, you get 2 with 4 left over. Now that we've mastered the basic arithmetic operations, there's something crucial we need to understand about how Java performs calculations, and that's operator precedence. This is one of the most important concepts in programming because it determines the order in which operations are performed, and getting it wrong can lead to completely unexpected results. Let me demonstrate this with our precedence demo class. I'm going to use the same 2 numbers we worked with before. Number 1 set to 20 and number 2 set to 8, so we can focus purely on understanding how precedence works. First, let me show you what happens when we mix different operators in a single expression. I'm creating a variable called result1 that calculates number 1 plus number 2 times 3. Now you might think this gives us 20 plus 8, which is 28, then times 3, which would be 84. But that's not what happens. Java follows mathematical rules where multiplication has higher precedence than addition. So it actually calculates 8 times 3 first, getting 24, then adds 20, giving us 44. To prove this point, I'm creating result2 with the exact same numbers. But this time, I'm using parentheses to force the addition to happen first. Now we get number 1 plus number 2 in parentheses times 3. The parentheses override the normal precedence rules, so we get 20 plus 8 equals 28. Then times 3 equals 84. For result 3, I'm demonstrating what happens when operators have the same precedence level. With number 1 times number 2 divided by 4, both multiplication and division have equal priority, so Java evaluates them from left to right. It calculates 20 times 8 first, getting 160, then divides by 4, giving us 40. Finally, result 4 shows another left-to-right example with number 1 plus number 2 minus 5. Addition and subtraction have equal precedence, so we go left to right. 20 plus 8 equals 28, then minus 5 equals 23. Now I'll display all these results with clear formatting to show exactly what calculations were performed. I'm printing out each operation with the numbers, operators, and results, along with explanatory notes about which rule applied. This makes it easy to see how precedence and parentheses affected each calculation. Let's execute this program to see operator precedence in action. Perfect. The output clearly demonstrates how precedence affects our calculations. Notice that result 1 gives us 44, not 84, proving that multiplication happened before addition. Result 2 gives us 84 because the parentheses forced addition to happen first. Result 3 shows left-to-right evaluation with 40 as the result, and result 4 gives us 23 from the left-to-right addition and subtraction. When I print out all these results, you'll see how the same numbers can produce completely different answers depending on operator precedence and the use of parentheses. This is why understanding precedence is absolutely essential for writing correct programs. Now we need to tackle something that confuses many Java beginners but is absolutely essential to understand, and that's type promotion in arithmetic. This is what happens when Java mixes different number types in calculations, and understanding this will save you from many frustrating bugs. Let me demonstrate this with our type promotion demo class. This time, instead of working with just integers, I'm going to create variables of different numeric types to show you how Java handles mixed calculations. First, I'll create an integer called number 1 with the value 20. This is our familiar whole number. Next, I'm creating a double called decimal 1 with the value 15.5. Notice that doubles can store decimal places with high precision. Then I'll create a float called decimal 2 with the value 4.2, and I'm adding the F suffix to tell Java this is specifically a float value. Finally, I'm creating a long called big number with the value 1,000,000 using the L suffix to indicate this is a long integer. Let me print out all these values so we can see what we're working with, including our integer, double, float, and long values. Now comes the fascinating part. Watch what happens when I mix these different types and calculations. Java has built-in rules for type promotion that automatically convert smaller types to larger types to prevent data loss. For result 1, I'm adding our integer number 1 to our double decimal 1. When Java sees an integer mixed with a double, it automatically promotes the integer to a double before doing the calculation, so we get a double result. In result 2, I'm multiplying our double decimal 1 by our float decimal 2. Here's something interesting. Even though float seems smaller than double, Java promotes the float to a double because double has higher precision. The result is a double. For result 3, I'm adding our integer number 1 to our long big number. Since long can hold larger values than int, Java promotes the integer to a long, and we get a long result. Finally, result 4 shows integer division with a twist. I'm dividing our integer number 1 by our double decimal 1. Because we're mixing an integer with a double, Java promotes the integer to a double, and now we get true decimal division instead of integer division. Now I'll display all these results with clear formatting to show exactly what types were mixed and what the outcomes were. I'm printing out each operation showing the original values, the operation performed, and the final result, along with notes about which types were involved. Let's run this program to see type promotion in action. Great. The output shows us our different variable types and their values. Then we see the magic of type promotion at work. Result 1 shows 35.5 because our integer was promoted to a double. Result 2 gives us 65.1, where the float was promoted to a double. Result 3 shows 1,020,000 because our integer was promoted to a long. And result 4 gives us 1.29. Instead of integer division, we got precise decimal division because the integer was promoted to a double. When I display all these results, you'll see how Java automatically handles the type conversions for us. The key rule to remember is that Java always promotes to the wider type, which is the one that can hold more data without losing precision. This prevents data loss, but means you need to be aware of what type your results will be. Finally, let's address what might be the biggest gotcha in Java arithmetic, and that's integer division. This catches even experienced programmers off guard and is responsible for countless bugs in real-world applications. Understanding this concept will save you hours of debugging frustration. Let me show you the problem with our integer division demo class. I'm going to use two simple integers, num1 set to 25 and num2 set to 4. These seem like innocent numbers, but they're about to demonstrate a major pitfall. First, let me display our starting numbers so we can see exactly what we're working with. I'll print out the values of num1 and num2 and add some spacing for clarity. When I perform what looks like a straightforward division, num1 divided by num2, you might expect to get 6.25 as the result. After all, 25 divided by 4 is 6.25, right? But here's the problem. I'm storing the result in an integer variable called integer result. Here's what happens. Java sees that both num1 and num2 are integers, so it performs integer division. This means it calculates the division but then throws away everything after the decimal point. 25 divided by 4 gives us 6.25, but Java discards the 0.25 and gives us just 6. The decimal portion is completely lost. This is a huge source of bugs because the code looks perfectly correct, but you're losing precision without realizing it. So how do we fix this? I'll show you 3 approaches, including one common mistake. Solution 1 is to cast one of the numbers to a double before the division. I'm creating solution 1 by casting num1 to a double, then dividing by num2. Now Java sees a double divided by an integer, promotes the integer to a double, and performs decimal division. We get the correct result, which is 6.25. Solution 2 is to use double literals from the start. Instead of integer variables, I'm directly using 25.0 divided by 4.0. Since both numbers are doubles, Java performs decimal division and gives us the precise result. Now here's the wrong way that many beginners try. In wrong solution, I'm casting the entire result to a double after the division has already happened. But this is too late! Java has already performed the integer division and thrown away the decimal places. Casting 6 to a double just gives us 6.0 because the precision is already lost forever. Let's execute this final program to see integer division and its solutions in action. Perfect. This output clearly demonstrates the integer division problem and its solutions. The integer division gives us just 6, losing the decimal portion completely. Solution 1 with casting gives us the correct 6.25. Solution 2 with double literals also gives us 6.25. But notice the wrong solution. Even though we cast to double, we still get 6.0 because the precision was already lost during the integer division. The key lesson here is that the data types of your operands determine what kind of division Java performs. If you need decimal results, make sure at least one of your numbers is a double or float before the division happens. Integer division has its uses, but you need to be intentional about when you use it. Congratulations. You've now mastered the fundamental arithmetic operations in Java. Let's quickly recap what we've learned today. We started with basic arithmetic operators, including addition, subtraction, multiplication, division, and the modulus operator. These form the foundation of all mathematical calculations in your programs. We then explored operator precedence, learning how Java follows mathematical rules to determine the order of operations. Remember that multiplication and division have higher precedence than addition and subtraction, and parentheses can override the natural order. Next, we discovered type promotion, which is Java's automatic system for converting smaller numeric types to larger ones during mixed calculations. This prevents data loss, but means you need to understand what type your results will be. Finally, we tackled the notorious integer division problem. When both operands are integers, Java performs integer division and discards decimal places. To get precise results, ensure at least one operand is a double or float before the division occurs. These concepts are absolutely fundamental to Java programming. Every real-world application relies on these arithmetic operations, so mastering them now will serve you well throughout your programming journey. In our next lesson, we'll build on these foundations to explore more advanced mathematical operations and problem-solving techniques. Keep practicing with different numbers and combinations because the more you work with these concepts, the more natural they'll become.